Okay, so can I start now?
Yes, you can start.
Okay, so hello everyone. Thank you so much for the invitation. It's great to have the opportunity to talk about my research today. So I changed the title of the talk a little bit. Originally, I planned to talk about just scheduling in multi-hop networks, but I decided to make the talk a little bit more wide. So I'm going to talk about essentially three different papers to make it more accessible to people that might not be necessarily interested in the proofs of the results. So I'm going to talk about the variety of results and just give you some ideas about how the proof of different algorithms or results are. Okay, so why are we interested in scheduling packages with deadlines? Because we have all these new emerging applications in Internet of Things, vehicular networks, video conferencing, virtual reality, and so on, that now you need to provide some form of guarantee on the time that you deliver the packets from their sources to destinations. So this is what we call deadlines. And traditionally, of course, there's been a lot of work on designing scheduling algorithms, but they mostly focus on long-term throughput. So to design scheduling algorithms for these new applications, we need to come up with new algorithms that address the deadline guarantee requirements of this application. So in many of these applications, if you are not delivering the packets within a specific deadlines, that packet is discarded by the application. So I'm going to divide the talk to three parts. First, I'm going to talk about scheduling single hop traffic, and then I'm going to talk about the scheduling multi-hop traffic. So let's consider a model that you have packets with different deadlines arriving at different links into your network. So if I consider, for example, a situation like this, that you have a base station or access point with two links, 1 and 2. So for user 2, you have packets arriving over time. For user 1, you have packets arriving over time. And in this figure, I have used rectangles, and the length of the rectangles corresponds to the deadlines of packets. So for example, I have a packet with deadline 1 arriving for user 1. That means that you have to transmit this packet in one time slot, in the current time slot. Otherwise the packet will be expired. Similarly, the meaning of this green one is that the deadline of this packet is 2. So you have 2 time slots from the time that the packet arrives until the packet expires. So you could transmit this packet in the first time slot or in the second time slot because its deadline is 2. So over time, different packets with different deadlines could arrive at different links. And you have to make a decision that which packet should you transmit at any time. So the traffic pattern could have very complex characteristics. In general, you could have different patterns for your traffic. For example, you could have packets arriving according to this pattern, and then maybe the next time you have a packet with deadline 1 arriving for user 2 and a packet with deadline 2 arriving at user 1. And the next time, maybe you have 2 packets with deadline 3 and deadline 2 arriving at user 2 and a packet with deadline 1 arriving at user 1. So the important thing here is that different number of packets with different deadlines could arrive for any of the users. And you need to make a decision about how you're going to prioritize transmission of this or the scheduling of these packets. So for example, here, I could have a very complex arrival and deadline process or traffic process when you have patterns. And maybe you transition between different patterns according to different transition probabilities. So you could have a Markov process like that generates the traffic into your network. And of course, we do not know how this Markov process look like. So I'm going to model the interference in my network. I'm going to consider what is called the standard interference graph. So you could have, so each link in the network has a buffer that contains the unexpired packets and their remaining deadlines. So as I mentioned, when the packets expired, you could just drop those packets. So every link in the network has a buffer that contains the unexpired packets and their remaining deadlines, because if the packet remains in the network, you have to reduce this remaining deadline. And then you have to make a scheduling decision. So scheduling is you have to select a set of links to transmit packets from at any time slot. And then, of course, the set of links that you select, they need to have unexpired packets in their buffers. And of course, the set of links that you select shouldn't interfere with each other. So if I'm considering this notion of a standard interference graph, for example, I could have what is called the collocated network. So here I have 7 links, or I have 5 links. And then at any time, you could transmit only one of them to transmit because the links are interfering with each other. Or I could have a more general interference graph, like the figure on the left, when you could have links 1, 3, and 5 activating at the same time. So essentially, this is the standard interference graph notion that if I put an edge between 2 links, that means that these links cannot be activated at the same time. They interfere with each other. Okay, so the set of links that you're selecting shouldn't share any edge in this interference graph, or should be independent sets of this interference graph. This is a standard model for modeling, interference in wireless networks. So what is our notion of performance? So the notion of performance is efficiency ratio or approximation ratio. So as I mentioned, we are interested in measuring only, those packets that you transmit within their deadlines. So we could extend the notion of throughput. We could call it timely throughput for every link L, which is, so I use RL to denote this timely throughput, essentially is the average rate that you're transmitting packets from link L, according to their deadlines. So the average rate of timely delivery of packets from every link. Now, if you give me any scheduling policy mu, of course, there is, given a traffic, there is a certain set of, timely throughputs that you could achieve for the different links in your network. So this is what I denote by lambda of mu. So given a scheduling policy mu, there is a set of timely throughputs that you could achieve for different links. And then your goal could be, okay, if I, for example, let's say there is a weight or reward for every packet. So if I look at link L, suppose if you're delivering a packet of link L within its deadline, I'm giving you a reward WL, let's say. So then your goal should be, okay, I want to maximize my average reward for the packets that are delivered on time. So you could try to maximize an objective like that. So given set of weights or rewards, you're trying to maximize the average, your average reward, right? And you only get the reward if you're delivering the packet before its deadline. Or you could consider an equivalent goal, which is, if I give you a vector R, so I give you an RL for every link, can you guarantee a timely throughput of at least RL for every link? So I either give you a target vector for timely delivery, or I give you a vector of weights and I ask you to maximize your average reward. And of course, in both objectives, you have to deliver the packets before their deadlines. And of course, these 2 objectives are equivalent. So if I give you an online algorithm that makes the scheduling decisions, and let's say that online algorithm achieves a gamma factor of the optimal average reward. Okay, so of course, I do not know what is the optimal solution, because to get the optimal objective value, you need to know the characteristics of your traffic that I do not know. So I do not know how the traffic look like, what packets what deadlines arrive in future. I need to design an online algorithm, and I'm going to compare the performance of this online algorithm with the optimal algorithm that knows everything ahead of time. So this is what I call G star. So if I give you an online algorithm that achieves gamma fraction of the optimal reward, then that algorithm can also achieve, this is easy to show, that can achieve a gamma fraction of what we call the real-time capacity region. So let's say this set here is the set of all the timely throughputs that can be achieved potentially. And then this online algorithm that gives me this approximation ratio can achieve any rate, any timely throughput vector, which is within a factor gamma of the capacity region or real-time capacity region of the network. So these 2 objectives are equivalent. And the way that to make the objectives, to see the connection between them is that you could, if you want to convert an algorithm for this problem to an algorithm for achieving a certain timely throughput, you could just define weights to be deficit counters. Okay, so for every link, you could define a weight that we call deficit that essentially measures how much service you owe to that link to meet its timely throughput requirement. So if the timely throughput requirement for link L is RL, every time you're going to increase that by RL per time slot. And then every time I have a packet departure within a deadline, I'm going to reduce this deficit by 1. So it's like a virtual queue essentially. And this is known that using these virtual queues, essentially these two objectives are equivalent. So essentially you could view these deficits as dual variables for the primal problem. So you could view these virtual counters or virtual queues as dual variables, and that's how these two optimizations are equivalent. So please feel free to stop me at any time. So feel free to unmute yourself and ask your question if you have any question. So because the problem, is really important, there's been a sequence of works within the past 15 years on this problem. There is work on frame-based traffic models. So in the frame-based traffic models, they assume that you could divide time to frames, and then at the beginning of every frame, all the arrivals and deadlines for the packets that arrive in during this frame. So if I have access to that knowledge, then the optimal decision is you could just solve some form of dynamic programming or max weight matching algorithm, essentially, that tells you which packet you should transmit at any time. So you could solve a dynamic programming because you know everything ahead of time. And then whatever you do not schedule at the end of the frame will be dropped. And similar thing repeats at the beginning of the next frame. So at the beginning of the next frame, the assumption is that you know what's going to arrive during that frame ahead of time. And then you could solve a dynamic program. But of course, we do not want to make assumptions like that because we do not know what's going to arrive in future. So we want to solve this problem under general assumptions on the traffic without making assumptions about how the traffic look like. There's been also work on greedy maximal scheduling. So greedy maximal scheduling is an algorithm as follows. Well, you look at the weight or the deficit of the packets into your network, and then you select the packet that has the largest weight. Okay, so you don't care about the packet's deadline. You just select the packet that has the largest weight and you transfer, and then you remove the interfering links that interfere from this link, and then you repeat the same thing. At the end, you end up with a maximal schedule. Okay, so this is what people call greedy maximal scheduling, or sometimes call it longest deficit first algorithm. So if I use a simple algorithm, greedy algorithm like that, this has been shown in this paper that, if you consider i.i.d. traffic, then the efficiency ratio of this algorithm is at least 1/1 plus beta. So what is beta? Beta depends on the topology of your interference graph. So beta is essentially what we call interference degree of the graph, which is the maximum number of links that can be scheduled simultaneously out of a link and its neighbors. So if I consider interference graph like this figure here, beta is 3 because if I consider this red node and its neighbors, I can only select 3 of them to transmit at the same time. So the interference degree here is 3. So efficiency ratio is 1/1 plus beta. And if you consider Markovian traffic, so if the traffic is not i.i.d. but has Markovian dependencies, the efficiency ratio could be shown to be smaller than 1/1 plus a square root of beta. Okay, so these are the results which are known for greedy maximal scheduling. Greedy maximal scheduling, as I mentioned, doesn't care about the deadlines, and its performance could be very bad. So we could construct example. Let's consider a very, very simple case. Let's say I have a network with 2 links, links 1 and link 2, that interfere with each other. So at any time, I have to select only one of the links for transmission. Then you could consider very simple, traffic patterns that are really bad if I'm doing greedy scheduling. So let's say you have a packet with deadline 1 arriving at link 1, and then you have a packet with deadline 2 arriving at link 2. If the weight of packet with deadline 2 is larger than the weight of this yellow packet, greedy maximal scheduling going to select packet 2 for scheduling in the current time slot, and as a result will drop this yellow packet because yellow packet has deadline 1 and is going to expire. In the next time, you could force the algorithm by choosing the deficits or weight that again it makes a wrong decision. So it would, for example, you have a packet with deadline 2 arriving at link 1, and instead of selecting this packet, again, maximum weight scheduling would select a packet that has a larger deficit or larger weight. It would select this packet that has a longer weight and has a longer weight and has a longer deadline. But that's a wrong decision, because if I transmit this yellow packet, you will have to drop the green packet with deadline 1. So essentially, you could construct examples that if you just you're choosing the greedy maximal scheduling, the greedy maximal scheduling will drop half of the packets. But of course, here you could transmit all the packets between their deadlines, right? I can transmit this yellow packet right now, and then I have one time slot to transmit the green packet. And similarly here, I can transmit the yellow packet in here. I can transmit the green packet here, and then I have one time slot left to transmit the yellow packet. So the optimal algorithm can transmit all the packets, but greedy maximal scheduling actually would drop half of the packets. So this shows that the performance is 50% efficiency ratio. In the classical non-real-time scheduling, there's been, of course, the famous max weight scheduling algorithm, or MWS. So in the max weight algorithm, essentially, you select a schedule which has the maximum weight. So if I consider a weight for every link, then you just select a schedule that has the maximum summation of links that are in part of that schedule, right? This is called maximum weight scheduling policy. So you select a schedule that has the maximum weight, and the weight of the schedule is the summation of the weight of the links which are part of that schedule. In the non-real-time setting, if you're only interested in maximize the throughput and there is no deadline, of course, the maximum weight scheduling is being shown by Tesselius and Efremides in 90s that this is the throughput optimal algorithm and can achieve any rate in the non-real-time capacity region. So this is throughput optimal, essentially. And then if you come up with some approximation to this max weight, suppose you come up with some psi approximation to max weight that will achieve a psi fraction of the real-time capacity region. So these are the known results from max weight scheduling, but this holds for non-real time. Max weight could be really inefficient if you're using it for real-time scheduling because packets expire because of the deadlines. But we can still, if you're using algorithms that rely on weights or deficits for scheduling without paying attention to deadlines, you could still get something out of those algorithms for real-time scheduling. And here is the result. So if you give me a policy that, let's say, provides a psi approximation to the max weight algorithm, okay? So it returns a schedule to me that the summation of weights in that schedule is a psi fraction of the optimal max weight. Then if I use this policy for real-time scheduling, then packets could have deadlines. The efficiency ratio would be psi divided by psi plus 1. So compared to this result, that if you give me a psi approximation to max weight, then you could achieve psi fraction in non-real-time scheduling. Here, you actually achieve this fraction, psi over 1 plus psi. Okay. So what are some of the corollaries of this theorem is, well, if you use max weight scheduling, when psi equal to 1, then the efficiency ratio of max weight for scheduling real-time traffic with deadlines is actually half, because I also can give you a counterexample for the other side of this inequality. I can consider an example which is really bad for max weight and could give you the other direction of this inequality. So efficiency ratio of max weight scheduling for scheduling real-time traffic is half, okay? If you consider the greedy maximal scheduling, that I described that has lower complexity than max-weight scheduling, this one achieves an efficiency ratio which is 1/1 plus beta, when beta was the interference degree of the graph. So this result shows that you could convert if I don't care about the deadlines and I only care about the weights, like when you're scheduling, you ignore the deadlines of the packets and you do your scheduling decision based on weights. You could convert those algorithms to some real-time algorithms. They could characterize their performance for scheduling packets with deadlines through this theorem. There's also a prior work on worst-case approximation algorithm. So as I mentioned, I'm considering a stochastic traffic for how the packets are arriving to the network, but there's been also a sequence of works on the worst-case approximation algorithm. When you consider the worst-case sequence of packet arrivals and you're trying to maximize their reward, the sum of the rewards that you could collect by transmitting the packets during the deadlines. So there's a sequence of works here. I'm not going to go through them. So what is our solution? So our solution is something called MXND or adaptive mix. So let's say first I'm going to explain the algorithm in a collocated network. So in a collocated network, you could only transmit one packet at a time. Okay, so it's like an access point and a downlink from an access point, right? So you're transmitting multiple users. I can transmit one packet to one of the users in every time slot. Let's say you have only one frequency channel. So what I'm going to do, I'm going to order these packets according to their deadlines and deficits. So the x-axis is the deadlines of different packets, and the y-axis is their weights. Okay, so you get a picture like that. And then essentially for every link, you only consider the earliest deadline packet of every link. So you could eliminate the other packets from every link. And then we define a domination relationship. So I say link I is dominated by link J if the earliest deadline packet of link I has a greater deadline than the earliest deadline of packet of link J, and its weight is smaller. So in some sense, if I consider this packet 7 here, all the packets in this region are dominated by packet 7 because they have more flexibility. They have a higher deadline and also a smaller reward or a smaller weight. So you could identify these regions, and as a result of that, you could identify these non-dominated packets. So packet 2, 1, 3, 7, none of them is dominating the other one. And the optimal decision at any time is transmitting one of them. But of course, I do not know which one to transmit because the optimal decision depends on what packet is going to arrive in future. So what we're going to do, we're going to randomize over the choice of which of these non-dominated packets should we transmit according to some probabilities which are chosen very carefully. So this is how we're going to choose these probabilities, okay? So you look at the ratio between these two packets, between their weights, and then 1 minus that ratio give the probability of transmission for this packet. So you start assigning these probabilities based on the weights of these non-dominated packets, and then you keep track of what is the sum of probabilities. Of course, the sum of probabilities cannot go beyond 1. So at some point, you're going to terminate these probabilities and assign 0 to the rest of non-dominated packets. And then I'm going to transmit one of these packets randomly according to these probabilities. So let's say you choose packet number 3 to transmit at the current time slot. So you transmit packet 3, the region going to change, right? Now, maybe another packet become a non-dominated packet. And maybe you have packet arrival. Maybe, okay, so I randomize over these packets. Now, maybe this time you transmit packet number 2. You might have even packet arrivals. When you have packet arrivals, even this landscape is going to change. The set of non-dominated packets is going to change. So at any time, you're going to randomize over the set of non-dominated packets according to the probabilities, which depends on the weights of these non-dominated packets, and you transmit one of them randomly. And you just repeat the same thing in every time slot. So what we have shown is that actually the efficiency ratio of something like that is at least 1 minus 1 over 8, which is almost 63%. So if you compare this with the performance of greedy maximal scheduling, or actually greedy maximal scheduling is the same as maximum weight scheduling in the collocated case, because you could only schedule one of the links. As I mentioned, in collocated case, the efficiency ratio of max weight or greedy maximal scheduling is at most 50%. So this one can give you 63%. So it's much better than greedy maximal scheduling or maximum weighted scheduling in collocated networks. We could extend this idea also to general graphs. So if I give you a general interference graph, then I'm going to randomize over the set of maximal schedules, because you could activate more than one link at any time. So you consider the set of packets that have unexpired packets in a set of links that have unexpired packets in their buffer. And then you consider what are the maximal schedules over this set of non-empty links. So I could have, for example, M1, M2, and M3 essentially here. And essentially, this gray nodes shows the nodes which are part of that maximal schedule. So for every maximal schedule, I can define a weight. And then I'm going to randomize over this maximal schedule with probabilities which are chosen very carefully based on the weights of this maximal schedules. And the way that you come up with this weight is that you're going to order the weight of, you're going to order this maximal schedule in the decreasing order of their weights. And then you're going to randomize according to this probability. So there's a constant here, which is, I call it subharmonic constant. It's like an average. It's very similar to harmonic average of a bunch of numbers. So it's like a subharmonic average of your maximal schedules. And then I'm just going to randomize over these schedules according to these probabilities. So I'm going to randomize over the first n maximal schedules here, when n is essentially is the largest number that give a valid probability distribution here. Okay, so the key point here is that instead of just choosing the maximum weighted schedule, I'm going to randomize over the choice of maximal schedules. And if I choose my probabilities carefully, this is the efficiency ratio that you're going to get. So we could show that the efficiency ratio is given by this. So it depends on the number of maximal schedules times the 2 times the number of maximal schedules minus 1. So this is definitely greater than half. As I mentioned, if you just use the maximum weighted scheduling, you achieve 50%. To give you an idea about whether this result is good, let's consider a star topology. So I have a green node at the middle and I have a bunch of blue nodes. So at any time, you could either transmit from the green node, because green node is interfering with all the blue nodes, or you could select all the blue nodes to transmit from. So I have 2 maximal schedules here, the green schedule and the blue schedule. If you use greedy maximal scheduling that either select green one or select the blue schedule, we know that as I mentioned, if you can, in the worst case, in the Markovian case, the efficiency ratio of greedy maximal scheduling would be less than 1 over the square root of k plus 1. So k is the size, essentially is the number of these leaf nodes here. So if the network becomes larger and larger, the efficiency ratio of greedy maximal scheduling goes to 0. Versus if I'm using this algorithm that I'm just randomizing over the green schedule and blue schedule, you could, because now m, essentially the cardinality of m is 2. So the efficiency ratio would be at least 2 over 3, which is much better. So I'm not going to go over the proof details of this, but essentially the proof technique for all these randomized algorithms is through a careful gain comparison technique. So in the collocated network, let's say you have 2 packets ij here. And let's say your algorithm makes a wrong decision, which is different from the optimal algorithm. So perhaps optimal transmit packet j, but algorithm transmit packet I. Now packet j is in the buffer of algorithm and packet I is the buffer of optimal. What we're going to do, we're going to essentially make the states of the optimal and algorithm the same. So we're going to either inject packets to optimal, or allow optimal to transmit extra packets. But we also make sure that these changes are advantageous for the optimal. So sometimes we give extra reward to the optimal algorithm. So by doing that, I make sure that in every time slot, the state of optimal and algorithm is the same. And I keep track of what is the expected compensation that I had to give to the optimal algorithm. So that's a rough idea behind this gain analysis technique in the collocated network. You could see the details in the paper. we could do the similar type of gain analysis in the general network. Let's say the optimal policy transmit this maximal schedule, this gray 1,5, nodes 1,5, but your randomized algorithm selects a different maximal schedule, MJ. What we're going to do, we make the buffers the same. So to make the buffers the same, I have to allow this optimal to transfer extra packets, which are in MJ, not in MI. And I have to insert packets that are in MI, but not in MJ, back into the buffer of, the optimal policy. So by doing these operations, you could make the state, the buffer the same, but also I make sure that these operations are advantageous. So of course, these operations are advantageous for optimal, but also I have to match the deficits or weights in the optimal and your algorithm. And to match those deficits, I have to give some extra reward or compensation to optimal to make sure that these operations are still advantageous for the optimal, no matter what's going to happen in future. And then I can bound the expected compensation, okay? So this is like a very rough idea of how this gain analysis and the proofs work. If you want to see the details, you could look at the paper. There are some simple simulation results here that that actually verify what I talked about. So you could construct various simulation results that show that if you're relying on these greedy algorithms or maximum weight scheduling algorithms in the setting of real-time scheduling, the performance could be really bad. So for example, if I consider, as I mentioned, a collocated network, those algorithms would drop half of the packets. So the efficiency ratio or delivery ratio cannot be greater than 50%, versus this green one corresponds to the algorithm, the randomized algorithm I described, and they can achieve delivery ratios which are up to close to 1. Okay. If there are no questions, let me also talk about this. All these algorithms can also be extended to the case that your channels are unreliable. So you could have fading channels. Let's say you have packets arriving over time, and every packet has a deadline. And also inside these circles, I have denoted the probability of success of transmitting over the channel at that time. So essentially, in every link at any time, if you're transmitting, the probability of success is QL of T. So then you have to make a decision that at any time, let's say you could only select either the green, here at this time slot, you could either select the green packet or the pink packet or the yellow packet for transmission. And how do you make those decisions? Because the success probabilities are different at any time, and the deadlines of the packets are different, and you do not know what packets and how the channel look like in future, because I'm not assuming that the channel is stationary or anything. The success probabilities would change in the future. How can I make these decisions in an online manner? So we could extend the randomization technique that I talked about. Essentially, what we're going to do, if you consider, we could define the notion of domination between the links or maximal schedules. We could extend them to consider this channel success probabilities. And the way to do that, you could consider, for example, let's say you consider a collocated network, right? And let's say at any time, only one of the links can transmit because the links are collocated and interfering with each other. And let's say if you're transmitting from a link at any time, for now, let's say the probability of success is Q. There's a probability of success is Q. I'm just going to modify. So I'm going to consider the set of non-dominated packets as I described. And then I'm going to assign these probabilities that now depend on the success probability and also the relative ratio of the non-dominated packets. So again, if I randomize over the set of non-dominated packets, you could achieve an efficiency ratio, which is now, of course, a function of the success probability or fading probability. But if you compare this with the maximum weighted scheduling gives you efficiency ratio of 50%, but this randomization technique gives you an efficiency ratio that ranges from 50% to 63%, depending on what is the value of your success probability Q. And you could extend this also for the general case. Let's say you have a general interference graph, and the links might have different success probabilities at any time. Then you could define a weight now. So for any link, instead of just looking at the, the weight or deficit, you could just look at the product of weight and the success probability. And that's how you define essentially the weight of every schedule. And again, you could use this weight. You could just plug them in the probabilities that I described for randomization over the maximal schedules. And that gives you an efficiency ratio, which is greater than 50%. You could come up with low complexity versions of this algorithm. I'm not going to bother you with this.
Quick question. Hi, David. This is Lingjia Liu. Thanks very much for the great discussion. So, I mean, for this overfitting channel, do you have any specific assumptions on what kind of fitting channel it is?
No. So it could be, as I mentioned, it could be okay. So the assumption here is that this is a Markov traffic fading process. So the fading channel, essentially the channel reliability probability, could evolve as a Markov process that I do not know how does it look like. So you could have, you could jump between different states, and I'm not assuming that I know the transition probabilities of this Markov chain.
Great. Well, this is very general then. Very good.
Yeah, it is very general. So actually, the whole purpose of this talk is to show that there is, I mean, I changed the title of the talk. It's called Power of Randomization. So once in the presence of all these uncertainties, and when you do not know how things look like in future, we're going to randomize. And if you're choosing the probability of randomization carefully, you're going to get non-trivial gains from these randomized algorithms.
I completely agree. This is a very great insight. In fact, actually, from the coding theory and random coding, and also actually we are doing some kind of a neural network. We are showing actually with the Professor Li Zhongzhen from MIT, actually, we're also showing some kind of random generalization of the weights. Is not actually a bad idea. And in fact, what you are saying here kind of echoes this.
Very interesting.
Fantastic, fantastic. I really appreciate it. Sorry for being late because we have actually student visitation today.
No problem.
Yeah. Thank you.
Yeah, of course. Yeah. So yeah, you could even, so let me ignore this coloring variant and talk about it very like a distributed, like this probably the most stupid algorithm that you could come up with. Let's call it distributed myopic policy. So what is this algorithm? Well, again, you have packet arriving. I do not even know how the channel look like in future. What are the deadlines of the packets? I consider something which is very, very simple. So every link that has packets to transmit, it runs an exponential timer with rate nu. Okay, so it has an exponential timer. It's like an exponential backoff essentially that we learn in a basic CSMA course. And that's how you do. And then whenever a timer of a node expires, it's going to transmit a kind of a message and inform its neighbors that be careful, like that I'm going to transmit a data packet next, right? And those neighbors going to be silent. So to do this randomized, let's myopic randomized, this is a totally distributed algorithm, right? You're going to select a schedule, which is totally random. And then those links that are part of this schedule, they would transmit their earliest deadline packets. So that's the whole algorithm. And if we use this, you could achieve an efficiency ratio, which is 1/1 plus delta. When delta is essentially the maximum degree of this graph. So you could do this, you could get this approximation ratio, and this is irrespective of what's going to happen in the future in terms of the channel gain, in terms of the channel success probabilities and what packets arrive with what deadlines. So it's a very naive algorithm, but they still give you some non-trivial performance. Okay, so essentially, I went quickly over this. Everything that I talked about so far was for single hop traffic. The situation becomes much more complex if I go to multi-hop traffic. Because in the multi-hop traffic now, every packet could go, through multiple links to go from source to destination. And then if you have multiple flows in the network, I have to decide what packet to transmit at any link at each time. So the space of decisions is much more complex. And of course, as these packets with different deadlines go through the network, the deadline is going to change. And the priority of this packet is going to change. So the red, for example, here shows packets that have reached the end of the deadlines. And then if you do not schedule them, you have to drop them, right? And so to show you, okay, for now, let's consider the multi-hop setting, but let's forget about the wireless interference. Okay, so let's just consider multi-hop network. Links have capacities, of course, but there is no wireless interference among the links of this multi-hop network. The problem is still super complex. So let's say if I give you a source, let's say the source and destination of this green packet are these two nodes, and then this packet has deadline 5. There are many ways, exponentially many ways of transmitting this packet from here to here. So you could transmit the packet over this link, over this path, or maybe you transmit the packet over this path, and then next time you transmit over this link, and then there is a safe loop here. That means that you wait here for one extra time slot, and then you transmit. So here, you have to specify at what time you transmit the packet over every link. If I just give you the route is not enough, because I have to satisfy the deadlines of the packets. So let's consider this setting. So I give you a multi-hop network. There are source destination pairs here. So every fellow has a source. Let's say you have a source 1, and the packets that generated from source S1, they have to go to destination Z2. You have different source destination pairs. Sorry, S1 has to go to Z1, S2 has to go to Z2, S3 has to go to Z3. So you have fellows, the different source and destinations, and the packets of these fellows have different deadlines and different weights. And the packets for every fellow that I call type arrive according to some stochastic process with some rate. So for type J or fellow J, the rate of packet arrival is A bar J. And every link here has a strict capacity CL. Every link L has a strict capacity CL. What is my goal? I want to maximize the weighted number of timely delivered packets that go from their sources to destinations before their deadline expires. And what are my constraints? I have to satisfy the capacity constraint. The number of scheduled packet over a link L at the time T cannot be greater than CL. So that's the problem that I want to solve. What is our performance metric? Again, it's in terms of approximation ratio or efficiency ratio. If I give you a random sequence of arrivals, there's an optimal reward for the optimal offline policy. And I look at the expected optimal reward under the optimal policy. Expectation is over the random sequence of arrivals. And then you give me an online algorithm, I see what is the expected reward that you achieve if I'm using your online algorithm. So if your online algorithm achieves gamma fraction of the optimal reward, I say, your approximation ratio is gamma. So it's like an average approximation ratio. As I mentioned here, we should extend the notion of route, because route shouldn't just include the sequence of links, it should also kind of include the sequence of times. So, let's say you have 3 packets A, B, C, and the destination of all these packets is V, and the deadlines is 2. Then you make decisions. So if you're transmitting these packets, let's say the capacity of every link here is 1. So I can transmit packet B over this link, and packet A has to remain at the node U itself. So I say I include UU. So I include a safe loop here. The meaning of that is that packet A is remaining at the node U. And I'm including link UA here. That means that packet B has transmitted over link UA, right? And packet C, I included link AV here because packet C was transmitted over this link. So to do this in safe loops or links, you could construct a sequence of links essentially here that if the packets follow those sequence, they're going to get to their destinations within the deadline. So for example, packet C reached the deadline within 1 time slot, and I included a safe loop VV here. That means that the packet V just stays at the node V itself. Okay, so this is what I call route schedule. Again, coming up with there are exponentially many route schedules in general. So it's just a definition. There's been work also on the scheduling in multi-hop networks with end-to-end deadlines, but majority of them, they consider the worst case traffic. So I have listed a bunch of them here. I'm not going to go through the details of them, but essentially all these results are as follows. They are in terms of a quantity, which is called the length of the longest route of a packet in the network. So you look at your network, and you get what is the length of the longest route that the packet could follow in your network. Of course, because the maximum deadline of every packet is d max. And in every time that you transmit, you consume one time step, the maximum route cannot be greater than d max. So L is a quantity which is bounded by the maximum deadline of the packet. Now, all these results are in terms of L. They say, I can give you an algorithm that achieves 1 over log L approximation ratio if your minimum capacity also scales logarithmically with L. So all these results look like this. So if you're giving me a capacity, minimum link capacity in your network, which is at least log L, your capacity, if your L start growing, your efficiency ratio goes to 0 as 1 over log L. Okay. There's been also work on the kind of an average traffic case, but they kind of consider the relaxation of this problem. When the constraints are relaxed, or you look at some asymptotic regimes. For example, a work by Kumar and his student, they look at, you have a stochastic packet arrivals, but then they relax the capacity constraint that only the expected number of packets that you transmit over a link has to be less than CL. So the question is that what would happen if the number of packets that you transmit over a link goes above CL? Because you have to drop them in a real network, right? You either have to queue them that consume deadline, or you have to drop them. That means that you're losing reward. Or they consider a setting when the minimum capacity go to infinity or the arrival rate go to infinity. So I'm going to talk about essentially an idea or an algorithm that you do not have to do these relaxations, and you could solve the problem near optimally in the stochastic case. So we could show that if you consider the stochastic case without any relaxations, without capacity relaxations, you could solve the problem near optimally. So I can give you a 1 minus epsilon approximation ratio if the minimum capacity satisfies this condition. So I can give you, for example, let's say epsilon equal to half. That means that I can give you 50% approximation ratio if your Cmin is still logarithmic in L, right? So compared to those worst case algorithm, that shows that, given the same type of minimum capacity requirement, I can solve the problem near optimally. But instead of the worst case, I'm working in the stochastic case. So essentially, the key point here is that, again, if I'm working in a stochastic case, I can solve this problem more efficiently. So I'm going to talk about 2 algorithms. One of them is called, I'm going to go quickly over these algorithms because I think I'm running out of time, but there are 2 algorithms. One of them assumes that you know the arrival rates, and I call that flow-based probabilistic forwarding. And the other one is in the case that you do not know the arrival rates, and you learn the arrival rates iteratively, and then you apply the algorithm 1, the probabilistic forwarding algorithm. Okay. So the flow-based probabilistic forwarding algorithm is as follows. So in every node, essentially, you have a set of forwarding probabilities that only depend on the packet type and the age of packets. That's it. Okay. And then once the packet arrives, if the age of packet is 0, so age means how long the packet has been in the system. That's what I mean by age. So if the age is 0, that means that the packet has generated at the node itself. If the age is 0, I'm just going to forward the packet over these links. So again, safe loop means that the packet remains at the node itself. So you're going to transmit over one of these links at random according to these probabilities. Okay. Or you're going to drop the packet otherwise. If the age is greater than 1, again, you're going to randomize over the set of links according to probabilities. Now that depends on the age of the packet because age is greater than 0. And then if you transmit the packet and the age is greater and the link capacity is violated over a link, you just drop that packet. Let me show an example. So let's say a packet arrives, a green packet arrives, and then you look at your forwarding probabilities that depend, because the age is 0, that's the meaning of this superscript 0 here. So you're going to just choose either one of these links uniform according to these probabilities, or you drop it with 1 minus the summation of these probabilities. So eta here is just some fixed constant. Let's say eta is something close to 1. Okay. And then let's say I choose link L3. So you're going to transmit the packet here. Now the age of the packet has increased to 1. Now this node looks at the probability, the forwarding probabilities for age equal to 1 packet, and then it's going to again either transmit over this link or transmit over this link at random. It's going to select one of them. Well, let's say you choose link L4. The packet is going to remain there. Now the age has increased to 2. I'm going to use the forwarding probabilities which correspond to age equal to 2 packets, and I'm going to forward it. Right? And so on. The key point here is that I'm using the same forwarding probabilities no matter independent of time. The forwarding probabilities only depend on the age. So let's say in the future, 2 more packets for type J arrive. I just use the same forwarding probabilities. So maybe you drop this one, and then you use the same forwarding probabilities, and then you forward this packet. How do you get the forwarding probabilities? You could just solve an LP. So I'm just going to maximize, as again, this algorithm assumes that I know the arrival rates. Then there's a version of algorithm that iterates between learning and solving this optimization. But here is the idea. So I solve essentially you're trying to maximize the weighted fraction of arriving packets that are being forwarded, during their deadlines. That's the meaning of this objective. And then you have a bunch of constraints. This constraint says, you have to satisfy the capacity constraints. And then this constraint says, the total forwarding probability at the source node has to be less than 1. And this constraint is just a fellow conservation. It says packets that arrive at a node at age tau minus 1, now the age is going to increase by 1. So it's a fellow conservation between the packets with age tau minus 1 and age tau. And this constraint just says packets have to originate from their sources and they have to end into their destination. So it's an LP, independent of the time horizon that you're going to solve the problem. You solve this LP and then you load these F probabilities into the nodes of your network. And they just do probabilistic forwarding according to these probabilities. And here is the result. We could show that this, if you choose that eta to be almost close to 1, or if you choose it to be 1 over 1 plus epsilon, that you could achieve 1 minus epsilon approximation ratio. So this algorithm is, on average, is nearly optimal if your Cmin satisfies that minimum capacity requirement. So the key point here is that, we could get, you choose any fixed epsilon here, you could get a constant approximation ratio as opposed to an approximation ratio that goes to 0 with L. So this is very different from the worst case. We could solve the problem much more efficiently in the stochastic case. As I mentioned, there's a version of this algorithm that doesn't assume that you know the knowledge of arrival rates. So you divide the time to phases, which are exponentially increasing. And in one phase, you learn the arrival rates and you use this estimated arrival rates. You feed them into your optimization, and then you come up with the optimal estimated forwarding probabilities for the next phase. And then here we could also show the performance of this dynamic algorithm that it still can achieve a 1 minus epsilon approximation, given the same condition on the Cmin. So there are extensions of this algorithm. I'm not going to go through them. So you do not need to assume that the packets are i.i.d. or stationary or anything like that. Let me ignore this. But what I'm going to talk about is what would happen in a real system. So in a real system, suppose you could design approximation algorithms based on the worst case traffic, or you have approximation algorithms based on the stochastic traffic. And I mentioned that, for example, for multi-hop network, we could solve the problem near optimally if I consider the stochastic case. But the traffic in a real network is not stochastic, right? Is non-stationary. Is not stationary, is non-stationary in a real network, and is not also worst case. There are some stationary behaviors, if you look at the traffic in real networks. So let me just show you some real simulations based on real data. So here, I'm just using something called IBM network that is a network of 19 routers with different links according to these topologies. And I use the traffic from a real data set. Is an IP traffic from a real data set from this paper. And I'm just mapping these IP addresses to the routers in this IBM network. And that's how I generate the traffic between different source destinations. I'm generating different number of flows between different routers in this IBM network. And I'm just following the arrival distribution, the trace of arrivals according to that data set. For example, if you look at 3 of the source destinations in this network, this is how the trace of data look like. So you could see that, okay, it's totally non-stationary. You see burst of traffic. So then if you look at the performance of, I'm going to compare the performance of my algorithms, which are based on stochastic, with the performance of the worst case traffic. So I'm simulating an algorithm called GLS-FE from this paper because, they have a huge extensive simulations, and they show that the algorithm is the best among the worst case algorithm that people have proposed so far. So as you could see here, x-axis is different link capacities, and the y-axis is the average reward per time slot. As you could see here, these are, so the red one and the green one are the dynamic versions of the algorithm that I described that do not assume the knowledge of traffic. And the blue one is this worst case based algorithm. As you could see here, the algorithms that I just presented, they significantly outperform the worst case algorithms, even in real traffic. So you do not have to assume that things are i.i.d. to get significant gain from the algorithm that we designed based on the stochastic traffic assumption. So let me ignore the proof. If you want to look at the proof details, you could look at the papers that I'm going to mention. But here's just a summary of this talk. So, I talked about essentially a bunch of results. In the single hop wireless networks, we saw that we could, through careful randomization over the maximal schedules, we could achieve a constant fraction of the real-time capacity region. And we do not have to solve any MDP. So I do not need to assume how the traffic look like in future, what are the channel conditions in future. And the techniques can be very useful even in other settings. For the multi-hop wired network, we saw that we could solve the problem almost near optimally if I consider stochastic traffic. And the algorithm actually performed well even in practical scenarios when you're, when you're dealing with real traffic traces. They perform much better than the algorithm that you design if you assume the worst case traffic. And here is just one slide from the takeaway message. About the takeaway message of this talk is, so scheduling problems in stochastic networks are becoming more and more combinatorial. You consider deadlines, you have channel conditions, you want to satisfy those deadlines or different type of constraints. And traditionally, people in the networking community relied on algorithms such as Maxwell algorithm or Lyapunov analysis, or solving, trying to solve some form of MDPs. But in the worst case setting, in the combinatorial optimizations, people have relied on approximation algorithms, amortized analysis, and LP relaxations. And there is a way to actually kind of unify these two approaches. And that's kind of what I did, essentially through randomization. There is a way to solve the combinatorial problems that happen in stochastic networks. Okay, so randomization can play a crucial role. And as you saw, we use randomization essentially to, in all the 3 parts of the talk, I either randomize over, the maximal schedules or non-dominated links, or I randomize, over I just use those flow-based probabilistic forwarding, just randomizing the transmission of packets over the outgoing links.
This is a great title.
Thank you so much.
Great title of the slides. Yeah.
Thank you so much. Yeah, and this is if you want to, as I mentioned, I decided just to go over the result and just talk a little bit about the message rather than just focusing on one paper and talk a whole lot about the proofs. But if you want to see the proofs, you could look at the papers. Thank you so much.
Thank you, Dr. Ghaderi, for your talk. Does anyone have any questions to ask?
Yeah, thank you, Dr. Ghaderi. That was a very interesting talk. I have a simple question. Maybe it's kind of ignorant. I'm just wondering if there's any connection in the algorithms you're talking about which unify the stochastic optimization, the combinatorial optimization, what's being talked about in the online learning literature. Maybe.
Definitely. So even if you consider the first problem that I talked about, right? Let's say you have packets that are generated according to some MDP, right? So you have packets and deadline according to some MDP, and we are in a model-free setting that I do not know the model of the MDP or model of the vault. And you're trying to come up with a control policy, right, that maximizes the average reward. So this is a well-defined RL problem, reinforcement learning problem. You could have solved it. You could train a neural network and then try to come up with an optimal policy as an output of that neural network using deep RL or something like that. That's not the approach that I took here. What I did here was that let's try to identify some structure for the problem, right? So I know that, okay, the optimal algorithm has to transmit from this set of non-dominated packets or from the set of maximal schedules. And then I'm just going to randomize over them. But that randomization is not uniformly at random. So essentially there's a key part of this analysis is how do you choose the probabilities of randomization? And I talked about the gain comparison technique during my talk very briefly. And essentially during that gain comparison, you could come up with what is the right choice of the probabilities that you could select for your randomization, that no matter what's going to happen in the future, you could still bound the performance of your randomized algorithm from optimal. So I would say this is a different way of solving this online learning problem, which could be very interesting because let's say you want to solve an MDP and you could identify a structure for the optimal solution, right? And I'm just saying that, okay, I do not know which decision is the optimal decision for your optimal algorithm. You have to randomize. How you should choose those randomization probabilities? You could use the gain analysis that I talked about to bound the performance of your randomized algorithm from the optimal solution to the MDP. So that could be of interest on its own, even if you're working on online learning.
Okay, yeah, that's very interesting, and it helped clarify some of the nuances I think I missed. Thank you, and great talk.
Thank you.
Are there other questions?
Yeah, hi. I had a question.
Sure.
I think, like you just mentioned, you instead of training like a neural network and formulating this as a deep RL problem, you kind of identified some structure in the network flows in the sense of identifying those probabilities for the single hop problem setup. So other than that kind of domain knowledge, let's say, is there any other domain knowledge that could be exploited to make the randomization a bit more structured in either the single hop or the multi-hop case?
I guess that's all I could came off it is that the problem is super complex, right? So if you could, the goal is that what detailed structure you could identify, and all I could identify was, look, if you have a collocated network, if you have like a base station and downlink, right? At any time you have to select one of the users to transfer packet to, there is a way to kind of identify a set of a structure that I have to select one of these non-dominated packets. Even if you consider the general case, all I could say was, you have to transmit from this maximal schedules, and then once you select the maximal schedule, transmit the earliest deadline packet from the link. That's all I could identify, right? It might be a way to kind of come up with a better characterization of the structure. I don't know, but that could be like a very interesting future question to ask. But that's all I could identify. But definitely, if you could come up with a better characterization, you could definitely improve the performance of these algorithms. That's definitely possible.
Right. Thank you.
Okay, if there are no other questions, thank you, Dr. Ghaderi, for taking time to speak to us. We enjoyed it. Sure,
no problem. Yeah, if you have any questions, as I mentioned, like I didn't talk about proofs or anything. The goal was that you might find some of these techniques useful, right? So scheduling doesn't have to be scheduling packets, right? let's say you want to solve some form of a scheduling problem in some other data centers or something like that have deadlines, or some form of combinatorial structure, you might find some of these techniques useful. So that was the kind of a goal of the talk. If you want to see the details, like the proof details, or if you find them useful, you want to see how the proof works and possibly apply it to your work, you could look at the papers that I cited. Thank you.
Thank you.
Thank you so much.